Welcome back to my Commodore 64 Games Memories video series. This is where I look at old games and some of the technical details behind them. Today we have Bangkok Knights, published in 1987 by System 3, coded by Nick Pelling, graphics by Hugh Riley, the main game music is by Rob Hubbard, and then the loading music is by Matt Gray. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel or sending me a super thanks. They are all always very much appreciated. Looking at the disk directory on the original disk image, we can see that it uses Paraprotect. Oh, and there's a CPU jam. Okay, it might just be this version of the emulator then. Let's try a recent version of Vice, a semi-recent version of Vice anyway. Okay, so this is a slightly more recent version of Vice with ICU64 integrated into it. I can see that it clears the whole of memory, or it writes through the whole of memory. Aha, okay. CPU jam is happening there too. Well, okay, it seems to be jumping into a whole bunch of memory up into kernel space, but it looks like the kernel has been switched off because the processor port, the 01 register in 0 page, is 35, so I think, if I remember rightly, that's all RAM with I/O enabled. So it seems to come from 0 page. Ooh, that's not good. It seems to be jumping through, from an RTI, it then goes through, okay, so FFE and FFF is actually pointing to right at the end of memory, and it seems to be executing through the end of memory to the start of 0 page, which is probably not valid code. That's a problem, isn't it? Okay, well, so let's debug this. Let's see why this issue happens on what I think is the original disk image from the original System 3 release, right? So let's have a look. Well, tracing back a little bit through the execution history, I can see a load accumulator with 3.5 in hex and storing it in 1. And then a JSR to 2AE there. There seems to be a little bit of a DECX, DECY, or DEX and DY instruction, which those two loops, they seem to waste a lot of time. Let's look back. Well, okay, so there's a JSR to EDFE, and just above it there's a JSR to EDDD. And that's in kernel space, but that, yeah, okay, so that's a send unlisten on the serial bus, so that, I think that's a legitimate kernel routine or part of a kernel routine which has been JSR to. EDDD, well, there's an EOR just before it, is probably sending a data byte, right? Yep, there we go. Output byte on serial bus. So it seems to be decrypting using that EOR and a DEC instruction. And then that seems to be using JSR EDDD to send something from the C64 to the drive. It's probably a memory execute command, to be honest. So it's sending a memory execute command, then an unlisten, which of course tells the drive to start executing the command. It then does a DEX and a DY loop, and then it does a JSR, but it turns off the kernel after that. So that tells me that the code after sending that command to the drive isn't expecting to use the kernel anymore because it's turned it off. So let's see what we get here. Yeah, so BA80 is at the moment it's filled memory look with a sequential pattern. That's not a valid code. So the code at 2AE, when it gets JSR2, probably expects to do a whole bunch of drive code, listening to drive code basically. So yes, it seems to do a whole bunch of register setup and then does a jump to B2, which is way down at the beginning of 0 page, or the middle of 0 page really. This code in the middle of 0 page seems to be the problem, where it's doing an RTI, perhaps, was it? And then getting to be in a bad place. Yeah, look, so it's storing, loading, EORing, and then doing an RTI. Okay. And if we step back from this, or step into this RTI, or step rather, in the machine code monitor, I mean, an RTI can be a good way of starting code, but this RTI seems to go to a really bad place. So it seems to be pulling bad values off the stack, doesn't it? So the RTI basically, what was it? It restores the processor status, and then it returns back to the code that was running before the interrupt. That's what it basically does. But this seems to be pulling bad values off from the stack and then JSRing into all sorts of really weird places that it shouldn't be JSRing and jumping to. So let's step back a little bit and actually see what command it's sending to the drive before it's trying to run some drive code but is failing to. So this is I think the command buffer and the drive memory. So we're doing an M8 colon 200 in hex, which tells the machine code monitor to dump the memory on device 8, which is the disk drive. And it's clear at the moment. So if I now do a memory, there we go. After all of these JSRs have executed, we can see that it's filled the drive's memory with a memory execute M-E and then a low and high address, which is low byte, high byte, 5 and 2, so that's 0205 in hex, and then follows a short sequence of what looks like machine code, obviously, and that's starting at address 205 in hex, of course, so that makes sense. That's 78, that's set interrupt, enabled flag, which stops interrupts. A5, OE, A5 is what, load X or something like that. So yeah, that's starting to run machine code on the drive code. So the drive starts executing code or wanting to execute code. But then the code on the C64 is really doing some really, really stupid stuff and is jamming the C64 CPU. So we need to find out why the C64 CPU is jamming, and then maybe the drive code will work. But let's put a breakpoint in the drive code. So we're setting up a range breakpoint on device 8, of course, which is device 8 is the drive in the machine code monitor. So we'll just start that off again, and we'll put some breakpoints there in the code so that we see which breakpoint hits first, whether or not the drive code breakpoint hits first or whether or not the C64's code breakpoint hits first. And oh look, the drive code breakpoint has hit first. So that, actually there's two little delay loops there on the C64 side. I can see a DEX-Y and another DEX-Y, DEX-X and DEX-Y delay loop. So there's two delay loops, and that gives enough time for the drive to start actually executing its code. So the C64 is just doing a little bit of delay there. The C64 is also doing some setup into zero page, which is probably setting up the drive code in the C64's lower zero page memory. The drive code doesn't look too difficult to understand. It's just setting up a job into job slot 4, and it's doing a read sector. That's job code 80 in hex. So the drive just reads a sector into memory and then just jumps straight to it with a jump 704. This is not difficult drive code. This is very easy drive code. It's very easy drive code because it's nicely using the existing job mechanism rather than trying to go lower level than the job mechanism, which is friendly for debugging purposes anyway. But we haven't hit the debug on the C64's code yet. So let's step into the drive code on the right-hand window here. I'm single-stepping the drive code just to get a feel for what it's doing. It's pulling load with C000, okay, and then storing it into 7. But X is 29, and that's going to be corrupting the load absolute comma X indexed comma X instruction there on the drive code at 729 because X is 729. So that store is 700 comma X is going to be causing a problem because that store is going to be changing it to 4C. Oh dear. 4C, if you remember your opcodes, is jump, right? So if we do one more step, then it will change the load C00, X to be a jump C00, which I don't think this code really wants to do, because it's going to be jumping to the start of the copyright 1982, 1985, 1987 Commodore Electronics Limited message there, plus the 2 hex bytes before it, which is not going to be good, right? I don't think the drive code is valid either. Oh dear, there's 2 problems. So yeah, what's going on here with this release? I mean, it is reading from the beginning of the drive's ROM code, right? But it's trying to store it back into the internal drive's RAM. And this copyright message doesn't contain executable code. It contains text. That's not good. So this is puzzling. Why is this, what looks like an original disk release, doing this? And is it a problem, really? I mean, is the drive code deliberately corrupting itself and deliberately doing it for obfuscation or protection? For protection purposes or obfuscation purposes, to try and make the drive code very difficult to debug? But the great thing is that we've got an emulator that can step each cycle. So yeah, no, running this kind of code, which is basically text, text bytes, is not right. So this is going to make the drive crash, right? And then the drive is going to go through its internal crash recovery mechanism. The CPU history on the C64 side just shows that it's doing that wait loop here still. So that wait loop with the DEX and the DY instructions there, it's doing it for, what is it, 65,536 cycles, approximately, give or take, because it's 2 loops of 220 times 256 bytes, 256 loops of 256 loops, so it's a nested loops twice. So yeah, that's 256 times 256, which is 65536, right? Anyway, so yeah, the drive code doesn't look great, but the C64 code also doesn't look great, because it turns off the ROM and then does that RTI and then tries to do some really weird stuff. So I think there's potentially 2 different problems here. So I just thought, in the emulator, it's using 1541-2 at the moment as a drive, but the original Commodore 1541 drive has the beginning of its ROM just filled with AA. I mean, there's a 97 at the beginning too, but most of the bytes are filled with AA here. So that changes the opcode, which is being replaced on the store accumulator C00, X or Y, right? It was indexed with. It changes it to TAX, which is a different opcode. On the drive code side. So on the drive code side, if it replaces it with TAX, maybe it is a ROM revision issue where this code, this release, only really worked on the original 1541 and doesn't work on a 1541-2 drive. So in the emulator, let's change the accumulator to equal to AA instead of the 4C that was read. And then let's let that change that instruction to TAX. There we go. We can see that now in the disassembly as it executes. And we'll just do, there we go, it does a TAX and a break. And it goes into the break handler on the drive. Okay, and the break handler on the drive pushes and pulls all the registers, does an RTI, and then it goes back to doing a store A 700, okay, and then it does the DEX, okay, and it does a BAPL, okay, and then the routine completes. So on an original 1541 with an original ROM, which has that specific ROM revision, this drive code doesn't fail. This drive code goes accidentally through to the break instruction handler, but then it returns, and then the code carries on, and it doesn't obliterate the beginning of the code at 700 in hex. This load and store indexed instruction in the drive code, it looks like it was just trying to copy over the initial drive boot code for whatever reason. Maybe it wanted to obliterate all traces of the drive code that it had just loaded and just executed from memory to make it harder to hack or something like that, perhaps. But yeah, so okay, so on an original 1541, the drive code succeeds, but succeeds by accidentally going through the BRK, the break instruction. Great. So that's one problem figured out. And then the drive code continues through and then tries to read sectors using, what was it, job 3. There, store A with 03, and then the CLI, and then a load A, 03 branch on minus 211. Yep. So that does a check for the job completing, and then it checks to make sure that the job code returns 1, I think it was. And then it jumps to the code at 744 in the drive code, which is kind of what we expect, right? Because I think the code at 744 in the drive code, yeah, okay. So I think it's returned a whole bunch of code that, or rather that's the stuff that was there previously, sorry. Well, okay, whoops, the kernel is enabled, right? The kernel's still enabled because 01 contains 37 rather than 35. Yep. Okay. So yeah, it's running that code still. So, but I think the C64 side is still going to go through and then try and do that weird stuff. But this jump on the drive code side, look, the drive code is basically doing stuff. The drive code looks like it's executing legitimate drive code. And the drive code looks like it's just waiting for a signal now from the C64. I think the C64 is still... there is a store indexed 8D, there, but there's an RTI instruction. I don't think... This code is not quite right on the C64 side still. Look, C64 side is still a bit wrong, but the drive code side seems to be working now with the original revision for the drive code wrong. We can see on the drive code that it's storing 0 into 1800, which is the VIA register, which is like the CIA, the complex interface adapter on the C64 side. But on the drive side, it's basically the same kind of chips which deal with the stepper motor and the heads and everything else like that. So now the drive is doing its wait for serial activity. Look, see, so it's waiting for activity on VIA1, which is the serial bus connection to the C64. So it's doing that load A with 4 and a bit and branch on equal instruction. So that's great. So the drive code side is now working. The C64 is still not cooperating. It's still doing this really weird sequence of instructions where it does a jump to B2 and then it does this RTI and then it fails. So why is the C64 side still failing? So when the code gets to this point at B2 and it does this RTI, it's expecting to pull the correct values from the stack that have been set up somewhere else. And it's going to be pulling these values from the stack, right? And it's going to be trying to RTI to these addresses here, plus also restore the processor status back to whatever it was. And then that's why we get to here. So this is not at all correct, right, on the C64 side. The stack is set up incorrectly. So I think a problem in the C64 side of the code is before this executes, there is something wrong on the stack. From a freshly reset emulator, let's type this command in manually rather than dumping the disk image on there, and then let's see what happens. So instead of dumping the disk image on there, which does the auto start stuff, let's just run it. Oh, well, look at that. The stack pointer, instead of F being F7, it's now F9 when it gets to this point in the code. And look at that. The stack is actually, oh, that's the drive stack. We are really more interested in what the C64's stack contains, right? Right, so the C64's stack. The values in the C64 stack are different because it's going to be using the stack pointer at F9 rather than F. Okay. Yeah. And that RTI has now gone into this code here now. It's gone into B2. Aha. And then this. Oh, look. Now the code is running correctly on the C64's side. And the drive code on the drive is actually running correctly as well. And the C64 has now correctly started running its drive code. Yeah, okay. So it's load. Yeah, so it's without the code, without the trailing colon. Of course, the emulator, when it does its auto start, adds a trailing colon to load star, 8, 1, and then it adds a colon onto the end. Adding a colon onto the end changes how much data is on the stack. It changes the memory state because the basic interpreter is interpreting a command line with an extra colon. There's extra stuff in there. It changes the memory state because the memory state for the command has changed compared to the memory state of the command without a colon. And so it looks like the Paraprotect bootloader code is assuming the memory state of the C64 is it's assuming that the memory state is as what it is after load star, 8, 1 without a colon, which is not friendly, right? That's not great at all. You don't want to assume that much of the C64's state. So let's set the emulated drive back to the original 1541 again now, so it runs the correct drive code. And then let's issue the boot command load star, 8, 1 without a colon. Very important. So the C64 side of the code is now going to be running, hopefully, its correct code. And the drive code is going to be running its correct code because it's recovered from accidentally executing that break instruction and then going through the break vector on the emulated 1541. And now, hopefully, by the time we get to that code there at 381, I'm hitting breakpoints on the drive code there, but let's get to 381 on the Commodore 64 side of things. Now let's get to this code here at 2AE, and 2AE, it should execute correctly now. Yes, it's hitting the code now in 0 page on the C64 side now, which is correctly, I think, correctly executing what looks like turbo load code. Okay. If you notice there, look, it's doing a load A with D012 and subtracting and carry testing and anding and stuff. It seems to be avoiding bad lines, which means that it's doing a bitwise timed read from the drive to avoid bad lines, which is very, very cool. It means that it's turbo loading bytes quicker from the drive because it's trying to avoid bad lines. It needs accurate timing. And now, yep, the drive code on the C64 side, or the drive communication code, and the drive code on the 1541, and they're both executing correctly now. Now you can see, look, as the C64 is waiting for stuff from the drive is doing things. It seems to be reading data from the drive. The C64 side, with the window on the left, look, it's doing a repeated bit and BPL there. That's waiting for a response from the drive, where the drive starts sending data back to the C64. So the C64 communication code now with the drive seems to be doing the correct load routine. Okay, good. And then it's getting here, and then it's storing into 8E and 8F indexed, indirected, Y. Seems to be loading stuff now. if we do an RTS, have we loaded anything that's going to be, well, it's loaded a whole chunk of data. Don't know where it loaded that to. BA, yay, there we go. BA80 now contains A200, which is, that's load X, right? Immediate. Is it BD00BB? Okay, that seems to be store absolute something. Absolute memory, there we go. So now it's starting to, yes, there we go, sorry, load absolute comma X. There we go, it's load X, load store, yeah, good. Now, great, so that was fun, not debugging the Paraprotect code issues. There were two issues. One, the drive code assumes the 1541 ROM revision rather than 1541-2, and also you have to not use a colon after load star 8.1. This music for this screen is fantastic. So this the initial release has this lovely dissolving, fading bitmap screen between the System 3 logo and the Bangkok Knights logo. Obviously, I think the sprites down at the bottom, there we go. The debug graphics map view there in ICU 64 clearly shows the sprites scrolling across the bottom of the screen. So that's animated sprites. We have these two bitmap screens in memory, and then of course the dissolve between them uses the third bank for displaying. So I really like this, that in this release from the original System 3 release on disk, they include the tape loader screens, right? And they include Matt Gray's awesome music as well. So let's continue on with the load now. Now, great, fantastic. The game actually works. We can actually get into the game. I can see little green sparkly read dots there happening. I think that's kind of like a feature of the Paraprotect code. It was doing an indexed compare comma X or something like that, right, with 0 page, which had no effect apart from introducing timing cycles to the code on the Paraprotect code. So here we go. It's loading the rest of the game code now. It seems to be loading 254 bytes chunks, which is correct because each sector on the disk is 256 bytes, but there is a next track and sector 2-byte header at the start of each sector, so that's quite expected. And there we go, we got a nice title screen with this dissolve between the title screen and the game is cool. I do quite like it. Interesting to note that there's no screen split, or at least the screen split is unusual in that it's actually not a boring, black bar. It's actually covered with something. I think it's probably covered with expanded sprites by the looks of it. But it's unusual. Usually the screen split between the pixel scrolling part of the screen and the score panel, usually that's just obscured by a black bar, right? But we can see that there's a ton of sprites in the debug graphics map there. That looks like compressed sprite data, right, doesn't it? We have some head sprites there, but I think this is the main display bank, of course. We can see that there are some dynamic sprites. And of course there was a fade dynamic sprite there for the dissolve between the screens there. We can see that in the bottom right hand corner, near the bottom right hand corner. There's also this kind of like horizontal line effect when the heads of the characters fade in and fade out. There we go, that's rather nice too. We'll investigate that, I think, in C64 Debug GUI. So I found a disk image, I think for a budget release a year after the initial System 3 release. If we have a look at the directory, it's very different. Instead of showing Paraprotect, it's just got a whole bunch of files there. If I load the first file and then list it, we can see, look, it's basic. There's no auto boot code, it's just basic. There's no protection there at all. Look, it's just using a load of the file name, 8,1 and doing a sys, and then another sys, and then a final sys after loading a whole bunch of 3 files. There's there really is no protection there at all. So this is just doing a normal boring kernel load of a whole bunch of files. It's just loading a whole bunch of data, so I think we'll whiz past this quite quickly because it's just doing a kernel load. So this budget release doesn't seem to have the nice System 3 and Bangkok Knights loading screen dissolve thing with the scrolly message down the bottom. It just has the bitmap screen being displayed without any of Matt Gray's awesome music, which is a shame, right? So here we are in C64 Debug GUI now with the unprotected budget release version of the game. Using the targeting cursor to scroll up and down, I could see that there were some sprites covering the screen, expanded sprites covering the screen for the screen split. I can see actually that there's two sprites. Ah, look. Did you see that? Did you see the dissolve sprites over the top of that screen there? So actually, the title screen has got quite a lot of sprites active. Look, each of these heads seems to use 2 sprites each, at least. We have to dissolve sprites over the top. Let's change the colors of the sprites so that instead of the dissolve being black, we can force it to be a different color, actually. I think this interface is quite fiddly to use sometimes. But if I use the targeting cursor, there we go, we can see now, instead of black, it's with colors, you see, and then the dissolve sprites come up in the debugging interface. There we go. So the sprites, when the screen dissolve effect happens, there are large overlaid sprites which just obscure the text behind and then reveal the changed text behind there. There we go. And of course, these sprites are duplicated going down the screen, so they're kind of like multiplexed as they go down the screen. So we'll just add a little note there into my debugging notes text file. Of course, I will be committing this debugging notes text file to source control in GitHub, and I will add a link into the video description below, so you can actually see all of the debug notes that I take when I'm working on this. So this is a rather nice dissolve effect. I think it shows that this game was at least, quite polished in terms of presentation. Now, if you've played this game before, of course, you will know that it has a surprising feature, and that's that the game actually uses quite large sprites for 2 of the players on the screen. It's a beat 'em up kind of thing, right? But it also has a scrolling background, which is surprising, but it also has sampled effects, some kind of like sampled speech and stuff like that. It's not great quality, but it's at least samples. So I think we'll have a look at that in a bit as well. The horizontal scaled sprites obscuring the screen split there don't seem to use all of the 8 sprites. It uses 7 horizontally expanded sprites there, I think. These heads, they are quite... Well, okay, so we can see from the debugger that it's X and Y expanded sprites. But look, aha, look. So this horizontal banded fade in and fade out of the sprite heads is actually caused by updating the sprite pointers on the raster lines as the sprites are being displayed. So it's alternating between a sprite definition with the correct sprite frame there and a sprite pointer definition which points to a blank sprite. And you can actually, as the sprite is being drawn, as it goes down the screen, you can actually change this on a raster line basis so that actually it's fetching different sprite data per raster line, so then you can either switch on, you can apparently switch on or switch off the sprite from drawing data, or you can change the drawn sprite data. So actually you can change the sprite halfway down, you can change its X position. But you can't normally change the Y position. That's normally fixed by the internal sprite logic of the bit. You can kind of tweak the sprite Y position or the height of the sprite, but that's really quite an unusual effect and not very well, or not very often used in games. Well, there are some games which use it, but not very often. It's very precisely timed, usually. Anyway, so let's go into the game, and oh look, the game we can see in the C64 Debug GUI editor. Oh yeah, I corrupted the sprites of the player. We're going to need to reload this. I pressed the wrong key in the screen editor, right? So let's load this again quickly and then get back to where we were. So we can see that there's quite a complex collection of sprites there for the player characters and also the intro announcer lady or whatever. So we've got all of these sprites. Now we can see that there are some quite large sprites, some tall sprites and also some expanded sprites in the X and Y. If I turn off the sprites, how do you turn off the sprites with this layers thing here? It's one of these, right? No, it's not this one. That's the picking one. That changes the color, yeah, for sure. That we're forcing in the other debug screen. Ah, there we go. So you can see there that with the screen split turned off, or with the sprites turned off, the sprites were obscuring the screen split, which is kind of what you expect, right? And then the sprites turned on again. You can see exactly how many multiplexed sprites there are. If I turn the sprites off, you can just see the bounding boxes. You can see where those sprites are being drawn. So there's that horizontal band fade in and fade out effect as well. Again, it's kind of like a teleporting effect or something like that, right? But I think that's a great effect to use in the game. And that was just turning the sprite pointer to a valid sprite or to a clear sprite with no pixels in it whatsoever. You know, you could get a transporter effect by, instead of pointing to a clear sprite straight away, you could point to some random noise or something like that, right? And then you could get kind of like a teleporter effect before you go to a clear sprite as well. So you could have done that. You could have had 3 or 4 frames that you change to. That would have been quite clever, I suppose. Anyway, as I'm moving the targeting cursor down the screen in the VIC debugger now, in the video chip debugger, you can see how the code starts executing compares with D012 and updating the sprite registers in the few cycles before as well. So this seems to be quite a mature, quite a robust sprite multiplexer, which uses interrupts, because we can see it's in an interrupt and it's doing an RTI, but it's also comparing the current code execution position with the raster position on the screen. And if the raster has already advanced so far, then it's not restarting an interrupt. I think it's going into the next multiplexer update. So I think it's got that optimization in there. And the multiplexer, I think, is quite mature in the way that it's handling the sprite expansions too. So there are some sprites which are multicolor and some sprites which are not, where they're high resolution. And there are some sprites which are expanded in the X, which is not too bad, but there are sprites expanded in the Y as well. So when you expand sprites in the Y, this changes when you can reuse that Y expanded sprite, because it's twice as tall, right? So you can't use it as often. So the multiplexer is actually taking this into account, and that's why I think it's actually quite a good example of a very mature and quite robust sprite multiplexer, is that it's dealing with all of this extra complexity. But we can see how the characters are drawn using the sprite multiplexing techniques as the targeting cursor moves up and down the screen. You can see which sprites are enabled and which are disabled when their multicolor or high-res configuration bits are stored into the VIC control registers of the sprites. You can see how their expansion registers are updated as well, or the expansion control registers are updated. So yeah, the screen split is obscured by horizontally expanded sprites. Quite unusual. Some games do, obviously this game does, but you know, quite unusual because there are complexities. If you use sprites to obscure the screen split, then it means that you have to make sure that the sprites that you're using in the middle of the game display period don't get too close to the horizontally expanded sprites. Because if you're using 7 horizontally expanded sprites to cover the whole width of the screen for the screen split, then you can't have any of the game character sprites for the main part of the game getting near that because you need time to update the sprite registers to point the sprites at the right position on the screen so they can start displaying, right? And you cannot easily abort the vertical draw of a sprite, so you have to make sure that your game sprites don't get near where you've got the screen split sprites. Okay, so okay, but this game, because it's a beat 'em up, you can, with the screen scrolling and you know, just limiting the movement of the two players, you can ensure that the players' sprites don't get near where your screen split sprites are. So that's fine for this type of game because the game sprites don't need to go over the screen split. Whereas in other games, if you've got like a vertically scrolling shooter, the enemies, the players, the bullets, explosions, whatever, right, they might need to go over the screen split. So that's why you don't normally see sprites covering the screen split. So let's look at the memory debug view now as we're playing through the game. And we got some, that's interesting. We see a great big scan through memory when there's a sample being played. So no surprise there, when the samples are being played, there's quite a lot of memory reads going on sequentially through memory. You would normally expect that kind of thing, right? Because sample data actually takes up quite a lot of memory, unless you compress it. But then if you compress it, you have to spend time decompressing it as you're reading through the data, and that takes CPU time. So the best place for a sample routine is in zero page because it allows the code to execute quicker, because you can use zero page increment, and there we go, increment instructions. And yeah, this is doing a store into D418. That's restoring the volume. What about, there we go, there's a load accumulator with 9B00 and a store with D418. And then there's also increment E3, decrement. Yeah, there we go. It's self-modifying the absolute memory address to load. And because the code is in zero page, the increment of the absolute memory address is an increment with zero page memory location rather than an absolute memory location, absolute memory address, which means that you're saving a cycle. So that's why I say that the best place to put sample update code is in zero page, because you spend fewer cycles, and because you have to update the samples, the volume register, to play the samples very rapidly throughout the entire frame. You have to do it, you know, at least 50, 100, 150 times a frame if you want good quality samples anyway. The best place to do that is in zero page so that you are saving cycles. So yeah, the sample playback code is there in memory in zero page. Let's just use a new version of ICE with ICU C64 to do a watch on store for D418. And you would hope that the music routine doesn't, but the sample playing routine does. Actually, let's do a breakpoint for the sample play routine for executing code in zero page. There we go, there's the code. Let's do a watch for store D418 now. So there's the code starting to execute in zero page, and then there we are. There's the store into D418 there. So this sample data, actually it seems to be using the low nibble for this sample. Look, it's doing a load accumulator, it's doing a load accumulator with $9200, and it's doing an AND with $0f, which is basically pulling the bottom 4 bits, the bottom nibble from the byte, and then storing it into the volume register. But the sample data in memory, well, if it's only using the lower nibble of sample data in memory, then that's not very efficient because it's wasting the upper nibble, the upper 4 bits. Is it? It's still just using the lower nibble. Okay, so normally sample code is, you know, sample code is usually different. Usually it's executing code which pulls the lower nibble and the higher nibble, and then because you've got two 4-bit nibbles, you can pack both 4-bit nibbles into one byte and you can alternate using them. Aha. Okay, so the game code seems to be, let's have a look. What is the game code doing here? Ah, okay, so the sample playback code is still just pulling the lower nibble here. What is this doing? Okay, let's see if we can find the code in the game which updates the sample play routine. Right, because this sample play routine wasn't doing shifts for the high nibble extraction. It's just doing an AND for the low nibble extraction. So let's see where this routine is being updated from. We'll just remove all of the other breakpoints and we'll just do watch store with E8, which is the store for the volume register. Okay, so there's a place in code. So before it started playing the sample, it put a whole bunch of code into 0 page at that memory location there, and then it's doing an RTS. And then there's code underneath it too. But it's pulling code from elsewhere in memory and putting it into 0 page. Huh. So it looks like there's two routines for updating the 0 page code. There's that routine in memory, which is the breakpoint is at 352F, right? And then that code just pulls out the lower nibble by doing the AND with #0f, okay? And then this sample playback code seems to be, there we go. That other sample playback code has placed into the same place in 0 page the different code which does the shifts, the 4 shifts, the 4 ASRA instructions, which shift the accumulator down 4 bits before storing it into the volume register. So there we go. There are two sample playback setup functions, and depending on the sample, it seems that it's either pulling the lower 4 bits or the upper 4 bits, the lower nibble or the upper nibble, basically in each byte. So that's the way that the samples are encoded into memory. You have one sample using the lower nibble and one sample using the higher nibble, and that seems to be the way it's packed. Okay, that's fine. It means that you don't need to, while you're playing samples, you don't need to swap between the lower nibble and the higher nibble all the time. Maybe that makes the sample playback code a little bit faster, but it makes the sample format harder to think about in memory. That's fine. So let's use the debug graphics map view to see if we can find map data. Scrolling through the memory, this looks like map data, right? Because it's using what looks like horizontal bands of map data with the correct character set that's being used for the game. So maybe we can extract this map data, right? Let's save a snapshot image, and if you've watched my videos previously, sometimes I use an external tool, Charpad, to load this snapshot. We'll just save the snapshot. We don't care about the disk image because we're not going to be using it to run the game again. We want to use it for Charpad. But yeah, I'm going to use Charpad to see if we can load the snapshot and then see if we can extract at least the currently drawn map. So we need to have the tile. We don't want the tile system enabled, right? So let's turn that off. So we don't want to proceed here. We want to turn off the tile system. Yep, there we go. Now what we can do is that now we have a, because I don't think that the map in the game is using a tile-based system, right? It looked like it was just horizontal strips of wider screen data. So we'll just see what we get, right? So we'll open the dump file first. There we go. We'll set the character set to be C00, which is where it was in memory. That's fine. Now we'll just scroll through until we find the place where we think the map is. It was maybe A800. That's a good round memory address to start with. We'll change the map width now until we get something which is makes sense, right, visibly in this view here. So, you know, I think the screen is wider than 48 characters. So let's keep on going until we actually seem to get good data. I mean, that looked somewhat sensible, but it wasn't completely sensible because there were weird lines between each one. So let's make it wider and wider and wider until we seem to get a matchup. That's not quite matching up yet, is it? Let's keep on going. This is like tuning in a TV on a TV signal, right? And changing the speed of the refresh. Aha, there we are. Let's change the start address in memory. So it's OA7 instead of A800. That's fine. The map height. Well, let's change the map height so that we have a good degree of map height. I don't know how tall the virtual map screen is. We'll just use like a sensible round value for now. We can just edit that to be like 177 bytes, 177 characters. It's not that, because that would be filling a large proportion of the C64's memory, but we'll just do that. And then there we go. This seems to be the currently loaded game background, extracted from the Vice snapshot. It's obviously not as big as 177 characters tall. It's actually, let's have a look at the coordinate base here. It is actually probably 40 odd characters tall or something like that. But anyway, yeah, so there we go. That's how you can use Charpad to extract background from the game. So we now know the background from the game is stored in memory in that format. We know we can see where all of the sprites are. We can see that the sprites are dynamically updating for a lot of the sprites as the characters are being drawn, and that's not a surprise, right? There's an awful lot of graphical data going into the player sprites there. There's quite a number of different moves. Oh, that's interesting. On the far left-hand side of the screen there, we've got some animating characters for birds in the background. They look like birds swooping around, right? That's quite cool. That's a nice little graphical touch there in the background data for the level. So that's dynamic characters and dynamic sprites. A good multiplexer, and the multiplexer is really very cool in this game, and that was also fixing the Paraprotect turbo loader as well for the disc edition. I'd like to take this opportunity to thank my subscribers and my supporters for this channel. You are the boxing gloves that help protect my fists while I'm punching my enemies in the face. I hope that doesn't get me demonetized, but hey, there we go. So thank you very much for watching. If you like these kind of deep technical dive videos into all Commodore 64 retro games, then please do consider liking or subscribing to my channel. And I hope to catch you around next time. Have a great day, evening, or night, wherever you are.